My thought process has been focused on making AlphaEvolve and JEPA practically useful for heavy construction machinery. Initially, my ideas centered on autonomy, how these AI systems could grant excavators and bulldozers more independent control. I aimed to sketch out clear, detailed scenarios to demonstrate how JEPA could translate high-level goals from AlphaEvolve into sophisticated, nuanced control strategies for machines on the ground. I then delved deeper into these scenarios, concentrating on coordinated earth-moving. The concept was for AlphaEvolve to design the overall excavation plan, while JEPA would simulate real-world complexities like soil-machine interactions and equipment wear. The goal was to highlight how JEPA's detailed simulations could provide feedback to AlphaEvolve, enabling it to fine-tune plans for peak efficiency and minimal machine damage, always considering real-world challenges. Subsequently, I pushed to refine these use cases for more intricate problems, moving beyond basic machine control. My focus shifted to complex situations, such as fully autonomous earth-moving with multiple machines working in concert, and optimizing fleet-wide fuel efficiency and wear. The core idea was AlphaEvolve orchestrating the entire operation, from task assignment to real-time adjustments, with JEPA providing detailed simulations of soil dynamics, machine wear, and sensor data. This marked a stronger emphasis on real-world constraints. From there, I developed more distinct use case scenarios, prioritizing aspects like optimizing fleet-wide operations, integrating human operators, and even using AI to propose new machine designs. For autonomous earth-moving, I concentrated on coordinating multiple machines for precise terrain modifications. AlphaEvolve would act as the conductor, with JEPA simulating critical details like soil interactions, machine wear, and unpredictable site conditions. My objective was to clearly demonstrate AlphaEvolve's strategic planning power alongside JEPA's detailed simulation capabilities. This led me to a highly detailed scenario, orchestrating complex construction, specifically autonomous earth-moving. I envisioned AlphaEvolve managing a mixed fleet, excavators, bulldozers, etc., while considering varying soil conditions and unexpected obstacles. JEPA's crucial role would be to simulate the intricacies of soil interaction, machine dynamics, and sensor data. I particularly focused on how JEPA's simulations could create a feedback loop, informing AlphaEvolve's strategic planning and allowing for real-time adjustments to boost efficiency and safety. It became clear that more specific and challenging examples were needed, especially ones that truly grasped the construction machine focus, as some earlier examples were too generic. I knew I had to provide something truly detailed and complex, showcasing the powerful synergy between AlphaEvolve and JEPA with excavators, bulldozers, and similar equipment. That's what brought me to this advanced example: fully autonomous, multi-machine coordinated site preparation and earth-moving. The challenge I set was a massive construction project, such as preparing the foundation for a new airport, a large industrial complex, or a complex highway interchange. This involves precise terrain sculpting, moving vast quantities of diverse earth materials, rock, clay, sand, to match a detailed 3D engineering plan. A heterogeneous fleet of machines, excavators, bulldozers, dump trucks, compactors, must work in concert. The environment is dynamic and unpredictable, with potential for unexpected underground obstacles, weather-induced changes in soil conditions, and the overarching need for safety even in a mostly autonomous setup. The optimization goals are multifaceted: speed, minimized fuel consumption and machine wear across the fleet, adherence to tight engineering tolerances, and paramount safety. Our smarter solution with AlphaEvolve and JEPA addresses this challenge as follows. AlphaEvolve acts as the master site operations strategist, the fleet commander, crafting a comprehensive, adaptive, multi-layered operational strategy. First, through high-level task decomposition and sequencing, AlphaEvolve takes the 3D site plan and survey data, breaking down the entire earth-moving operation into a logical sequence of tasks and subtasks, determining the optimal order while considering dependencies. Then, with dynamic task allocation and resource management, AlphaEvolve designs algorithms to assign specific machines to tasks on the fly, considering their capabilities, location, fuel levels, maintenance status, and the work site state. It decides, for instance, which excavator loads which dump truck and its destination. Next, optimized path planning and traffic control is established for every machine. AlphaEvolve designs collision-free, efficient paths, considering current terrain, other machines, and no-go zones, solving a complex multi-agent pathfinding problem. For individual machine types, AlphaEvolve designs sophisticated, adaptive machine control policies. For excavators, this means optimal digging patterns to maximize fill rate and minimize energy per cubic meter, adapting to soil hardness. For bulldozers, it's optimal blade control for efficient pushing and precise grading. For dump trucks, it involves optimal acceleration and deceleration profiles to save fuel. Crucially, AlphaEvolve also designs contingency and anomaly response algorithms. These dictate how the fleet reacts to unforeseen events like hitting an unmovable boulder, a machine getting stuck, changes in soil stability, or sensor malfunctions, involving replanning, reallocating tasks, or flagging issues for human intervention. JEPA's advanced role is to be the hyper-realistic digital twin of the entire construction site and machine fleet, an incredibly detailed, physics-based simulation environment. JEPA-GeoPhysics, the terrain and soil interaction simulator, models the 3D terrain and updates it in real time as virtual machines operate. It simulates soil mechanics, how soils respond to digging, compact, affect stability, traction, and fuel use, and can predict issues like liquefaction or landslides, informing excavator control. JEPA-MachineDynamics, the individual machine simulator, models detailed kinematics, dynamics, powertrain, hydraulics, and soil interaction for each machine. It predicts fuel consumption, component stress, and wear rates based on AlphaEvolve's control policies and the simulated environment, and simulates sensor inputs. JEPA-FleetLogistics, the multi-agent interaction simulator, simulates the entire fleet operating concurrently, detecting potential collisions, material flow bottlenecks, and tracking overall progress. Optionally, JEPA Environmental, a weather and hazard simulator, could simulate how rain affects soil and traction, or how dust impacts sensors, testing the robustness of AlphaEvolve's strategies. The real power comes from their intricate synergy. It begins with iterative design and virtual commissioning. AlphaEvolve proposes a complete operational plan. JEPA then runs a full-scale, accelerated simulation of this plan on the virtual site, simulating days or weeks of operation in hours. JEPA provides rich, multifaceted performance feedback to AlphaEvolve on progress, accuracy, efficiency, fuel, operational hours, idle time, wear and tear on virtual machines, and safety, virtual collisions, stuck machines, handling of unexpected obstacles. This feedback loop drives the evolution of complex strategies. If JEPA shows inefficiencies, AlphaEvolve evolves its task allocation or control policies. If a virtual machine struggles, AlphaEvolve refines its algorithm or suggests alternative approaches. If JEPA simulates an obstacle, it tests AlphaEvolve's contingency algorithm. This system is also excellent for optimizing for emergent behaviors, allowing AlphaEvolve to design rules or incentives to prevent undesirable outcomes like machines unintentionally blocking each other. Critically, pre-training of control policies is possible. Individual machine control policies designed by AlphaEvolve can be extensively pre-trained and validated within JEPA's high-fidelity models before real-world deployment. This approach is significantly better and more complex for several reasons. It's a holistic system design, with AlphaEvolve designing the entire operational brain for complex, real-world, multi-machine tasks. It uses physics-rich simulation, as JEPA simulates complex physics crucial for realistic evaluation. It allows for anticipatory problem-solving, enabling AlphaEvolve to design robust strategies by simulating diverse and challenging scenarios. There's a massive reduction in real-world trial and error, making it feasible to test thousands of complex strategies virtually. And it addresses safety criticality, allowing exhaustive testing of safety protocols in a risk-free virtual environment. This kind of integrated system, I believe, could lead to construction sites that are significantly more efficient, faster, cheaper to operate, and safer, all by leveraging AI to design and manage operations at an unprecedented level of complexity and adaptiveness. That's the vision I'm working towards. Incorporating structural engineering principles, statics, moments, dynamics, is also vital, as construction often involves building structures or understanding machine structure interactions. This led me to consider how AlphaEvolve could design not just the operation, but the structure itself, with JEPA as a sophisticated virtual structural analysis lab. This brought forth the advanced example of AlphaEvolve designing an optimized, lightweight pedestrian bridge, with JEPA analyzing its structural integrity and constructability, including excavator assistance in construction. The challenge is multifaceted. The bridge must be structurally sound under various loads with minimal deflection/vibration, material efficient, aesthetically considered, and constructible, potentially with the excavator lifted prefabricated sections, making excavator stability part of the problem. Dynamic performance is also key. AlphaEvolve acts as the master structural architect and construction process designer. It can generate novel structural forms and optimize member sizing and material distribution. It considers connection details, construction sequencing, and temporary loads, especially during excavator lifts. JEPA then becomes an incredible virtual structural analysis lab and construction site simulator. JEPA statics analyzes structural equilibrium and strength. It applies static loads to AlphaEvolve's 3D bridge design and performs finite element analysis, FEA, to calculate internal forces, axial, shear, bending moments. The relationships here are that the rate of change of shear force along a beam relates to the distributed load, and the rate of change of bending moment equals the shear force. It calculates stresses, axial stress, direct force over area, bending stress, from moments, dependent on shape and distance from neutral axis, and shear stress, related to shear force on the cross-section. It also calculates deflections. For instance, the maximum deflection for a simply supported beam under uniform load can be precisely determined. All these are checked against allowable material stresses and core deflection limits. JEPA-Dynamics, the vibration and seismic/wind response analyzer, performs modal analysis to find natural frequencies and mode shapes to avoid resonance. This involves solving an equation relating the structure's stiffness and mass to its natural vibration characteristics. It can also do time history analysis using the full equation of motion, balancing external dynamic forces against the structure's inertial, damping, and stiffness forces over time, checking pedestrian comfort criteria. JEPA construction dynamics and machine interaction analyzes buildability and temporary stability. It simulates construction, especially critical excavator lifts. It checks excavator stability, ensuring tipping moment, calculated as segment weight times lift radius, doesn't exceed stabilizing moment, approximated by excavator/counterweight weight times its effective radius. It calculates loads on the partially completed structure during lifts, including dynamic factors. Effective lift force is segment weight times a dynamic factor, and analyzes temporary bracing. The synergy is an iterative design and analysis loop. AlphaEvolve proposes a design and construction plan. JEPA tests it virtually. JEPA statics checks stresses/deflections. JEPA dynamics checks frequencies/accelerations. JEPA construction dynamics checks lift stability/temporary stresses. Based on this multi-physics feedback, AlphaEvolve refines the design. This loop repeats, converging on a design satisfying all constraints. This is better and more complex because it's an integrated design and analysis. AlphaEvolve's creative proposals are immediately and rigorously tested. It's multi-physics optimization. It enables performance-based design. Constructability becomes a core design driver. It drastically reduces costly physical prototyping by catching flaws virtually. This deep integration allows exploration of a wider design space, leading to potentially groundbreaking structural solutions optimized across multiple dimensions, including how they are built using real-world machinery. That's the direction I'm pushing this research.